Hello, guys. Hello, everyone. Welcome back to ZUCMAP. This week we have Alex talking to us about quantum wine tasting. Enjoy.
Right, so can you hear me clearly? That's good. Okay, then I feel like this is not really working quite well. Is it? It is? Okay. Then welcome everyone to Quantum Wine Tasting, an introduction to quantum computation, your first quantum algorithm, and how we can use it to protect the integrity of Italian wine culture. I'm glad so many people came. First, we have a laser pointer. That's good. Thank you for organizing it. No, we'll manage. It doesn't have a laser pointer, but does it? It doesn't. Never mind, it's fine. I'll just click it on the thing. But thank you. Right, first a bit about me. My name is Alex. I study quantum engineering, and what I focus on in my life is quantum information theory and quantum information processing and algorithms. So exactly the kind of thing that we will talk about today. And there's going to be a first small trigger warning. If you're French, you might want to pop out for 5 minutes. I swear to God, this is just how the content of the presentation was presented to me. I don't want to make any statements about your personal culinary preferences. Right, so we will start with a bit of a riddle that has nothing to do with quantum. The poisoned wine problem. The Granduca della Toscana has a problem. French spies have infiltrated his wine cellar, which holds 1,000 barrels of fine Chianti wine. And they have exchanged 1 barrel for French wine. Consuming the slightest amount of French wine has a curious effect on Italians. For the first 30 days, no symptoms are noticeable. But as the wine slowly drains the culture from your body, the Italian dies on the 30th day with no chances of survival. The Granduca decides to test his barrels on some Italian prisoners, but he wants to get back to drinking as soon as possible, understandably. So he wants to be done with his experiment within 30 days. So what he can't do is have one prisoner taste from 1 barrel. If he doesn't die after 30 days, he goes on to the next. That's not allowed. You have to be done in 30 days, guaranteed. So how can he achieve this with the least amount of prisoners possible? Right, so one obvious thing would be to have 1 prisoner for each barrel, 1,000 prisoners, and then you look at who dies. A small improvement upon this would be to have 999 prisoners, and have everyone taste just 1 barrel, and then if no one dies, the one that's left over is the poisoned one, and if someone dies, you look at which barrel he drank from, and then that way you can still find the wine in 30 days. But the goal here is to do this with with the least number of prisoners possible. So take 2 minutes. I doubt that you'll solve the problem. If you solve the problem, you get a small piece of chocolate. I doubt you will, but what I would like to know is, what does your intuition tell you? What's the complexity class of this problem in n, where n is the number of wine barrels? So if I have n wine barrels, more or less, how does the number of prisoners I need scale? Question about the setup?
It wasn't a question.
No, you can talk about that with your partner, and then I would like to know what your intuition on this problem would be from just first hearing it. Question? The minimum number of days is 30 days. It's definitely right, because if you have 1 prisoner per barrel, it's 30 days. Okay. Right, so do we have some opinions? So who thinks it's quadratic? No one, good, because that would be very dumb, because it's at least linear, right? Because you can at least just take as many. Oh shit. When did I press this? Okay, well, now you know it's doable in log 2 of the number of prisoners, and there's a very elegant solution to this. So what you do is you label your barrels from 0 to 999 in binary. You need at most 10 digits for this. So on every barrel, you write out a number, a unique one. And then what you do is you take 10 empty wine glasses, one for each place of a digit. I did it here with 5 digits only, because I don't have that much space. But what is 5 here would be 10 in the problem. And what you do is now you take from each barrel and pour into some glasses. And what you do is you pour the kth wine into the ith glass if k has a 1 in the ith place. That sounds complicated, but it's not. For this barrel, it has 0, 1, 0, 1, 1. So what we would do is we would pour in these glasses some wine. Makes sense? Or you just take the binary representation, and then you do this for all the barrels, and then you have some mixtures. You mix the wine every time, obviously. And then what you do is you take 10 prisoners, one for each number of a digit, and you test the wine glass on the prisoner. And obviously the prisoner will die if and only if he drank French wine. If and only if he drank from a barrel, from a glass into which we poured poisoned wine. So he will die if that glass he drank from corresponds to 1 in the digit of the poisoned barrel. So if we do the experiment and after 30 days, the prisoner drinking from this, this, and this has died, then we know that the French barrel had to have had the number 11001. Right, who doesn't understand the solution? Everyone understands the solution. The Granduca can go back to drinking his wine and getting drunk. And we solved the riddle. I think it's a very elegant solution. It's a very parallel solution. So notice that we don't have to make any decisions based on prior outcomes. We just run everything together. And we've successfully identified our wine barrel with only using log of the number of barrels of prisoners. Right, so that wasn't quantum. I guess you're all here for something quantum. But keep this problem in mind, because it's the problem we're going to solve later with a quantum computer. So don't forget it. Now we're going to talk quantum computing. So a classical computer uses bits. A quantum computer, you might have heard, uses qubits. A bit is just anything that can only be in 2 states. So either a 1 or a 0, and it doesn't matter how we represent that physically in a computer. There's beautiful videos from Matt Parker, a YouTuber, who has built a computer from domino pieces. You can build a computer from literally anything. So as long as you have something that is either 1 or 0, you can make a bit out of it. Same goes for a qubit. A qubit is, instead of that, a 2-dimensional complex vector space. So a state of a qubit is just a 2-dimensional complex vector. Right? So it's just any element of C2 is a qubit. And then we choose a standard basis, 1, 0, 0, 1. The normal standard basis we know from linear algebra 1. And any vector we can write in that basis, and we just introduce a shorthand notation. If I write the 0 and the 1 with those weird brackets, then I mean the standard basis vector. That's just notation. All right, that is the state of a qubit. But the interesting thing about a qubit is measurement. We can't ever retrieve the whole state from the qubit. If the qubit is in some state V, we can't ever come to know what V was exactly. We can only measure the qubit, and then the result will be 1 or 0. And the probability of getting 1 or 0 is governed by the state it was in. If it's in a state V, 2-dimensional vector V, then the output being either 0 or 1 is the scalar product with the corresponding standard basis vector with the state V squared. So that's pretty straightforward, but we're going to do an example anyway. If you have a qubit in a state 1 over square root 2 times that, what would be the probability of measuring 0? Well, what we would have to do is, since we ask what's the probability of 0, we have to make the scalar product between the standard basis vector 0 and that. But the scalar product is bilinear, as you surely remember. So we can pull the sum and the square root 2 out of the scalar product, and we get this expression. Remember, the standard basis is orthonormal, so this is just 0, and this is just 1. And so we get 1/2, which makes sense, because what that means is that you're halfway in 0 and halfway in 1. Anyone not following so far? Good, because that's linear algebra 1. You should be fine with this. Now, what do we do if you have several qubits? It gets a tiny bit more complicated. Now, this set of possible states, if you have n qubits, is the tensor space, where you have an n-fold tensor product of C2s. And you work again with a standard basis. You know that the pure tensors span the tensor space. And the pure tensors we can write in the standard basis of just 1 qubit. So anything we can write out in the standard basis that I wrote here, where you replace the B1, B2, and so on with 1s and 0s. Right, so usually a standard basis vector is going to look a bit like this. And here again, we introduce shorthand notation. We don't want to write all the straight lines, and we don't want to write all the tensor products. So we're just going to write it like this. But when you see this, what I mean is this. Okay? So this is still just notation, and measurement works the same way. We can only ever get a bit string, 0s and 1s, as the result of a measurement. And the probability of that is the same as before, scalar product squared between the bit string we're asking the probability for and the state that we're in. So those are the basics. That is how a qubit is built up. But now we have to obviously be able to manipulate it somehow if we want to do computations. So the rule here, that just comes from physics, comes from the Schrödinger equation, is we can apply any unitary to our state. So if we are in some quantum state, what we can do as an operation on a state is we're allowed to apply unitary, a linear unitary as you know it from your linear algebra courses. And again, we'll do a simple example. One very famous gate that works only on 1 qubit, because it's 2-dimensional, right? Works only on 1 qubit is the Hadamard gate. It's this. You can test for yourself whether this is unitary or not. Spoiler alert, it is. And it maps the first standard basis vector to the state we had before, and the other one to the same state but with a minus. Okay, so that's pretty straightforward. And we can obviously, or we will obviously need to have unitaries acting on more qubits. And a very important example here would be the n-fold Hadamard gate, where you just apply a Hadamard gate to each single qubit. And we do, again, an example calculation. If we apply to the state 0, 0, well, what does that mean? Is we apply HH to both pure, well, to the pure tensor, so to both states of the product separately. So we get out this. The first line is just definitions that you should have seen in linear algebra when you did tensor product, which I know you did. And we get the tensor product between the two states we had before, and we can again use the bilinearity of the tensor product to get this. This calculation shouldn't be a problem for anyone, is it? It's not. Good. And if we look at this, what we observe, what we see, is we have basically all possible 2-bit bit strings summed together, right? And then a normalizing factor up front. Okay, and that we would actually get this every time that we apply the Hadamard to any standard basis vector. It's just that if we had had a 1 instead of a 0 in our initial bit string, we would get some minuses, because the Hadamard applied to the 1 gets a minus, gives a minus phase. We saw that in the definition. So it gets a bit ugly when we apply it to any other standard basis vector other than 0, 0. But we have a formula that takes care of the minuses for us. It looks intimidating at first, but it's not. This just says if we apply the Hadamard to any standard basis vector, so to any bit string vector, what we get is a normalizing factor, and then the sum over all possible bit strings as a state, as we have here. It's a sum over all possible bit strings. It's just some get a -1. And which ones get a -1? It's the ones where this turns out to be 1, or an odd number. And what I mean by y times x is bitwise addition. So you multiply everything bit by bit, and then you sum everything up, like the normal scalar product. If you want, I have the definition written on the blackboard, which is not moving. Which has turned off. Ah, there we go. The definition, if you need it, it says it over there. What we mean by multiplication is a scalar product type of thing, where we just multiply all the components, and then we sum everything up. Okay, so far so good. I see a lot of bored faces. we go over to the phase oracle. Yeah, now you're bored, but you're going to need it later. Now we go to the phase oracle. If we have any computable function, or if we have any function from the bit strings, 0, 1 to the n are the bit strings, 2, 0, or 1, there exists something called the phase oracle, which we will use later. And the phase oracle is pretty straightforward. You just give a -1 to those bit strings that would evaluate under f to 1, and you don't to those that don't. So UF, the phase oracle, is diagonal in the standard basis. Okay, why do we need this? It's a bit of a random definition, but it's actually important because we have a theorem from basic information processing, quantum information processing, which states that if we have a classical computer that can compute f, who here has done theoretical computer science already? Who has heard the words computable function? Okay, very few people have. So a computable function is just something where a computer could calculate it. It might be a long calculation, might be super expensive of a function simulating 1 billion molecules or something, but it exists. Okay, if we have some computable function that a classical computer could compute, then implementing this phase oracle in a quantum computer takes exactly as many operations. We can talk about this during the apéro. There exists a one-to-one correspondence between the classical gates you have to apply in order to compute f, and the quantum gates you have to apply in order to compute UF. So UF is like a quantum version of a computable function. Just to remember that. So if f is an expensive function that we want to avoid using, then we also want to avoid using UF. UF is equally as expensive as f to do. Okay, now let's test your attention spans, and let's go back to the problem we solved in the beginning. If we want to solve this with a quantum computer, we first have to formulate our problem more precisely, because what we had was just a funny thing with like French flags and wine, and everything was fun. But what is the mathematical problem that we were solving? And then we can ask ourselves, is there a better algorithm with a quantum computer? So at first, it looks like the problem we were solving was just unstructured search. Who has heard the words unstructured search before? Oh, not that many people. Interesting. The problem of unstructured search has a function that goes from some numbers to 0 or 1. Like before, the question would have been, is the kth barrel French? And then we have a function, aka testing the barrel on a prisoner, which is expensive to do. We want to avoid using that. Which answers the question. Is the kth barrel French? And then we get 0 or 1, yes or no, true or false, if we evaluate the barrel on a prisoner. And so we can write it like this. F of k is 1 if and only if k is x0 for some unknown x0, x0 being the index or the number of the poisoned barrel. Okay, and then checking f means evaluating f on a prisoner, and that is exactly what the problem states we want to avoid doing. So far, so good. So we could say our problem in the beginning was, given such a function, find me x0 with the least amount of evaluations of the function. But that is not quite what we can do. That is not quite right, because we can do more than that. Because we can't only test barrels, we can test mixtures of barrels, right? The solution included mixing wines together and then checking that. Okay, so we have to quantify what a mixture is. And let's say a mixture is an n-long bit string, where we have, it's not the same bit string as before with the binary number, but it's an n-long bit string. We have 1 bit for every barrel. And then we say the bit string representing the mixture should have a 1 for a given barrel if the barrel has been mixed into that mixture. That is how we imagine mixtures. Right, so we have 0, 1, 1, 0 would mean we didn't take of this barrel, we did take of this barrel, we did take of this barrel, and we didn't take of this barrel. Makes sense? Makes sense? Makes sense. Good. Okay, and then checking that is equally as expensive as evaluating it just for one barrel, right? Having a testing whether the prisoner dies of a mixture takes as long and takes as many prisoners as testing whether the prisoner dies of the entire barrel. So what we have access to actually is a function that takes a bit string that is n long, that takes a mixture, and tells us whether the mixture is poisoned. So it tells us whether the mixture has a 1 in the place corresponding to some unknown x0. Okay, so G would be saying, is the mixture poisoned? G of a mixture is 1, if and only if the mixture has a 1 in the place corresponding to the poisoned barrel, which we don't know. And thus we can write it in this form, G of B is just B x0. This is clear to everyone, I hope. Is it not? If you need more time, tell me. If I'm going too slow, tell me too. Don't think I'm going too slow. I'm not going too slow. Good. And then evaluating F is equally as expensive. So that is the correct formulation of a problem we had before. And now we can try to find a quantum algorithm that does this. How much time do I have left? I have plenty of time left. Oh, that's good. Okay, so now that is the statement of the problem that we want to solve. So now together we can go through the solution. This is your first quantum algorithm. This is 5 steps to finding the French barrel. We need n qubits. Every qubit is going to represent 1 bit of the mixture. And then we start in the state 0, 0, 0, 0, 0. Part of quantum computing and of the physical challenges of quantum computing is doing initialization, so we can assume that we are allowed to start in a state that we want. So we're allowed to start in a 0, 0, 0 state. So after step 1, our state is 0, 0, 0. I think you figured that out by yourselves. Then, second, to this we apply the Hadamard gate. If you don't remember the formula, I wrote it down here again, but I'm sure you're copying off the board, so you won't need it. We apply the Hadamard to this state, and what we get is just a superposition of all possible states. The thing we had before, if we apply Hadamard to the 0, 0, 0 standard basis vector, what we get is a normalized sum of all possible bit strings. So far, so good. That's a bit uglier than we started with. Now it's going to get a bit uglier still. Now we apply the phase oracle corresponding to the function g. So corresponding to the function that tells us whether a mixture is poisoned. Remember, the definition of the phase oracle was to give a -1 to those bit strings where the function evaluates to 1, and not a -1 to those where it evaluates to 0. So that's exactly what we get. That's why I need to use the stick. So that's exactly what we get. We apply the unitary to the state that we had before. Then, since the unitary is linear, we can draw it into the sum. So we just put it in front of a vector. And then we had this as the definition of UG over the basis vectors, otherwise linear. And then the G of B, we said we can rewrite that for our problem as just being the x0 width bit of the bit string. So far, so good. Then we have that, which is uglier still than the thing we had before. And now we apply the Hadamard again. So we apply the same formula again. So we do the same thing again, where we draw the linear gate into the sum and in front of the vector. And then to this, we apply the formula that we know what happens when we apply Hadamard to a standard basis vector. And we get this super disgusting long double sum. And you get the double sum because if you look at the formula for the Hadamard over here, if you just apply it to a vector, you get one sum, but then you're also summing over all the vectors that you apply it to. That's why you get 2 sums. I wonder how closely you're actually following the calculations, whether you're just being like, yeah, sure, or whether you're going through the terms and trying to find them out. Who has tried to go through the terms, struggling with the terms? A bit? Questions about any particular step? No? Okay, so you just get this state as a result. That state we'll call V4. It's just the state after the 4th step. Okay, so I have a bottle of Chianti at home. If you manage to tell me what state this is, you get that bottle. That's why it's called quantum wine tasting. Does anyone see where this is going? Terms cancel out very nicely. Yeah?
Wild guess, the binary representation of the Borrow number?
No, it's not. It can't be, because the binary representation of the number is pretty short. The length of that bit string is rounded up the log of n. But the binary representation is short. But this is at least it's going to be a vector in C2 tensored n times. So those are n long bit strings, and the binary representation isn't n long, it's log n long. Right? So it can't be that. Yeah. Oh, shit, now I owe you a bottle. Okay, well, you can pick that bottle up. That is exactly correct. Very good. What's your name? Jonas Hoffman. Okay, shout out. See, this is going to be recorded. You're going to go down in history. Very good. What's going to come out is the bit string that has zeros everywhere except in the poisoned place. Why? Well, let's calculate the probability of getting out this result, of getting out that bit string. Remember, what we have to do is find the scalar product. Now, I've been told that people will try to find errors on the slides, and there is an error on this slide. The probability is the absolute value of that squared. But let's first calculate this. So the probability is going to be the absolute value squared of this scalar product. We do the scalar product of the bit string that has zeros everywhere except link 0 with V4. Well, the scalar product is bilinear. We can get this out. We can get the sums out. So we just get this. Okay? But B is itself a standard basis vector. Right? By definition. And B prime is also a standard basis vector because we're summing over all the standard basis vectors. But this is an orthonormal basis. So this is only going to ever evaluate to 1 where B prime is big B and everything else is going to be 0. So we lose one of the sums. We lose the sum over B prime because that's just going to be big B. I like that sentence. So we're going to get 1 over 2 to the n times the sum of this. But, well, this is bitwise multiplication and then summing up, and big B only has 1 in the place corresponding to x0. So this is going to just select the x0 width entry of the bit string B. So B times B is just bx0. This is -1 to the B sub x0 squared, which is always going to be 1. So we're summing 1 over 2 to the n, sum over this 1, which is 1. Oh, there's another mistake. Here it should have a big N. Like here. Should be the same index here as here. That is bad. I'm sorry. My apologies. This should be the same sum. I hope that's clear. And this set has 2 to the n elements. So if you sum the 1 over the set, you get 2 to the n. 1 over 2 to the n times 2 to the n is 1. So the probability of measuring B is 1. Therefore, this must have been B in the first place, because we started from a normalized vector, only applied unitaries, i.e. isometries, and ended up with something that has scalar product with a basis vector which is 1. Therefore, V4 is equal to B. So we're guaranteed to measure the bit string having zeros everywhere except in the poisoned place. Questions? No questions. Very good. So, and once we have B, we can just count and see in what place the 1 stands. And then we know, okay, that is the place that is x0, and then we know which barrel is poisoned. So once we have that bit string, we're done. Okay, and the magic comes in through the fact that we only have to apply UG once. Right? We only have to do UG once, and the cost of doing UG is the same as doing G. So basically, we only have one function evaluation. And a function evaluation is the same as testing on a prisoner. So basically what we did is we took a quantum prisoner, fed it a superposition, and now the superposition is kind of gone. The superposition was here. We fed to the prisoner a superposition of states, a superposition of possible wine glasses, and what we got out was a result that tells us with certainty what x0 is. Okay, so if we sum everything together as a conclusion, we have this problem, mathematically stated, given a computable function, g from the bit strings to 0, 1, of this form for some unknown x0. We have to find x0 with the least possible amount of function evaluations. Classically, this can be done with this complexity. Whereas with a quantum computer, we're able to solve this problem with only one function evaluation, no matter how many qubits are necessary, no matter how many barrels we have in the wine cellar. Okay, so that's pretty cool. So that means that actually means that if we were to build a quantum computer, there are problems for which we are significantly better than a classical computer. Okay, there is still research being done, and it's still an unknown problem, how much better we can do. Obviously, this problem is in P. It's better than P. It's not only polynomial time, it's log time. And if you say, well, I'm interested in the complexity, not in n, but in the digits, number of digits of n, it's linear. So this problem is clearly in P, and something that is O of 1 is still in P. So what we haven't managed to prove is that we're able to take an NP problem and turn it into a P problem with a quantum computer. And if you manage to prove that, you'll probably get a Fields medal. Pretty sure. So it's still an open question for you guys to solve, and for me to solve also, for which problems this is applicable, and just how much of a speed up we can get. Whether we can ever get from an exponential or something that isn't polynomial down to something that is polynomial or even constant with a quantum computer. This is not known. But it's strongly believed that this is the case, and I'm sure you've heard of the prime factorization, which is doable in polynomial time on a quantum computer, and we don't know whether we can do that on a classical computer. Okay, and then very, very briefly, to wrap this up, the philosophy of a quantum algorithm, what is it that we actually just did? When can we do this? This is the big question, as I just alluded to. If you answered better than on this slide, you get a Fields medal, so try. First of all, parallelizability is king. What we had was a problem that was by definition parallel. We wanted not to have consecutive choices. We don't want to test some wines on some prisoners based on previous results, because we want to be done in 30 days. So we have what we call a parallelizable problem. We can have a lot of prisoners all being poisoned at the same time, instead of consecutively. So that is what we, okay, maybe that is not what we want, but parallelizability in general is what we want for a quantum algorithm. That's why a quantum algorithm is sometimes good. Because what we can do then is feed a superposition of all possible answers, even if that's exponentially huge, into some phase oracle, and get out an answer where everything cancels out nicely. If we had had a consecutive problem, we would have had to run that algorithm that I showed you with the 5 steps, maybe several times. And then that's no good, because every time UG appears, then we don't have really benefit. It's the parallelizability of the problem that gave us the advantage. Then second, the idea was we build a maximum superposition, we feed that into the phase oracle, and then we do a Hadamard again, and then everything happens to cancel out nicely. I've built a bit of an intuition about those things, because that's kind of what I do. But still, even to me, this feels like magic. That everything just cancels out quite this nicely feels like magic. This is a special case of something bigger, like there's always more that you can learn. But at the end of the day, it's very difficult to have an intuition about what just happened. What I get asked a lot by like my friends and family is, oh, you had a quantum algorithm. Can you tell me about this? How does it work? What's the idea? Well, what was just the idea here? There wasn't an idea, it just happens to work. If you have something like a binary search tree, you have something where you can say, well, I have nodes and I follow the nodes in this way, and there's some graph, and then you can have a key idea to explain to your mother on why your algorithm works. But here, it's just, well, -1 cancels out with -1 in a very nice way, and we get a good result. So it kind of feels like magic, so it's very difficult to come up with it. And there's not one explainable idea. Okay, so that is the essence of quantum algorithms. That is both the opportunity that we're presented with as the scientific community researching on quantum algorithms. There's a lot of problems that are well parallelizable. One of my favorite examples is the human brain. You are all, more or less, at least those who weren't in my exercise class, a good example of general intelligence. And that is obviously something we're trying to recreate with artificial intelligence. And the way your brain works is you have neurons that can only fire about 200 times per second. Because when the neuron fires and talks to another neuron, then some chemicals are exchanged. You have an action potential that goes to the cell. And then it has to calm down before it can do that again. So anything that you can think in 1 second, which is quite a lot of things. If you're like driving a car and you see a child and you decide to run it over or not, then that whole perception and decision process and evaluation of the situation, that's quite complex. Like if you manage to do this efficiently, Tesla will pay you a lot of money. And all those things that you can think in 1 second are therefore at most 200 consecutive calculations. So we have good reason to assume that AI is something that is very well parallelizable. Right? So that is a huge opportunity where parallelizability is king, that encompasses a very large spectrum of problems. But then again, the problem is, well, you need a brain large enough to come up with the quantum algorithm. And as we just saw, those are really weird, even to people who research them. So that is the ups and downs of quantum, and that concludes my talk. Thank you very much for coming. Thank you very much for your attention. I'd be happy to talk more in detail about the whole theorem with the phase oracle and its complexity later over the apéro. And if you have any questions, now's the time. Thank you.